Definition: a polygon is a closed plane figure whose sides are line segments that intersect only at the endpoints. The polygons we generally consider are convex. The angle measures of convex polygons are between 0 degrees and 180 degrees. Convex polygons are shown in Figure 2.28. Those in Figure 2.29 are concave. A line segment joining 2 points of a concave polygon can contain points in the exterior of the polygon. Thus, a concave polygon always has at least one reflex angle. Figure 2.30 shows some figures that aren't polygons at all. A concave polygon can have more than one reflex angle. Table 2.3 shows some special names for polygons with fixed numbers of sides. Table 2.3: polygon, number of sides, triangle, 3, quadrilateral, 4, pentagon, 5, hexagon, 6, heptagon, 7, octagon, 8, nonagon, 9, decagon, 10. With Venn diagrams, the set of all objects under consideration is called the universe. If set P equals the set of all polygons is the universe, then we can describe sets T, which equals the set of triangles, and set Q, which equals the set of quadrilaterals, as subsets that lie within universe set P. Sets T and Q are described as disjoint because they have no elements in common. See Figure 2.31. A diagonal of a polygon is a line segment that joins two non-consecutive vertices. Figure 2.32 shows heptagon A, B, C, D, E, F, G, for which angle GAB, angle B, and angle BCD are some of the interior angles, and angle 1, angle 2, and angle 3 are some of the exterior angles. Line segment AB, line segment BC, and line segment CD are some of the sides of the heptagon, because these join consecutive vertices. Because a diagonal joins non-consecutive vertices of A, B, C, D, E, F, G, line segment AC, line segment AD, and line segment AE are among the many diagonals of the polygon. Table 2.4. Triangle: 3 sides, 0 diagonals. Quadrilateral: 4 sides, 2 diagonals. Pentagon: 5 sides, 5 diagonals. Hexagon: 6 sides, 9 diagonals. When the number of sides of a polygon is small, we can list all diagonals by name. For pentagon ABCDE of Table 2.4, we see diagonals line segment AC, line segment AD, line segment BD, line segment BE, and line segment CE, a total of 5. As the number of sides increases, it becomes more difficult to count all the diagonals. Theorem 2.5.1. The total number of diagonals D in a polygon of n sides is given by the formula D equal to n times the quantity n minus 3, all divided by 2. Theorem 2.5.1 reaffirms the fact that a triangle has no diagonals when n equals 3. D equals 3 times the quantity 3 minus 3, all divided by 2, which equals 0. Use Theorem 2.5.1 to find the number of diagonals for any pentagon. Solution: to use the formula of Theorem 2.5.1, we note that n equals 5 in a pentagon. Then, the number of diagonals D will be equal to 5 times the quantity 5 minus 3, all divided by 2, which is equal to 5 times 2 divided by 2, which equals 5. The following theorem provides the formula for the sum of the interior angles of any polygon. Theorem 2.5.2. The sum, S, of the measures of the interior angles of a polygon with n sides is given by S equal to the quantity n minus 2 times 180 degrees. Note that n must be greater than 2 for any polygon. Find the sum of the measures of the interior angles of a hexagon. Then find the measure of each interior angle of an equal angular hexagon. Solution. For the hexagon, n equals 6, so the sum of the measures of the interior angles is s equal to 6 minus 2 times 180 degrees, or 4 times 180 degrees, or 720 degrees. In an equal angular hexagon, each of the 6 interior angles measures 720 degrees divided by 6, or 120 degrees. Figure 2.34 shows polygons that are, respectively, A. Equilateral, B. Equiangular, and C. Regular. Both sides and angles are congruent. Note the dashes that indicate congruent sides and the arcs that indicate congruent angles. Definition. A regular polygon is a polygon that is both equilateral and equiangular. The measure I of each interior angle of a regular polygon or equiangular polygon of n sides is capital I equals the quantity n minus 3 times 180 degrees, all divided by n. Find the measure of each interior angle of a ceramic floor tile in the shape of an equiangular octagon. Figure 2.35. Solution. For an octagon, n equals 8. Then, capital I equals the quantity 8 minus 3 times 180 degrees, all divided by 8, equals 6 times 180 degrees divided by 8, equals 1080 degrees divided by 8, capital I equals 135 degrees. Each interior angle of the tile measures 135 degrees. Corollary 2.5.4. The sum of the 4 interior angles of a quadrilateral is 360 degrees. Corollary 2.5.5. The sum of the measures of the exterior angles of a polygon, one at each vertex, is 360 degrees. Corollary 2.5.6. The measure, capital E, of each exterior angle of a regular polygon or equiangular polygon of n sides is capital E equals 360 degrees divided by n.